Okay, this is gonna work. Okay, test it. Then we can use that instead. Now. No, if I will get around to viscoelastic instabilities, I might ask someone to get me a tennis ball and a pair of scissors.
There's no rules. There are no rules.
Yeah, so maybe we should start again. So a quick announcement, the conference dinner is at 7 p.m. just across just there. We saw the table coming in. And so the next speaker is Efrati from the Weizmann Institute of Science, and he will talk about differential growth on geometric frustration.
Thank you. I'm very happy to be here, and I will start with quite a few slides to give some motivation and context of what we'll see. And I suspect I will be a bit less formal than the previous lectures, possibly, and I for sure would have the worst handwriting out of all the speakers that you saw. So I apologize for that in advance. If something becomes very unlegible, please let me know. So what I would like to tell you about is the intrinsic approach to differential growth and geometric frustration, many aspects of which we sort of heard and touched here. But I would like to tell you how we think of these things. And as the introduction, we will in principle ask, why do we need the intrinsic approach? What's wrong with the present, every common day approach, which is based on configurations and gradients of those configurations as we've saw in the previous days? And the answer to that question is intimately related to what is the fundamental difference between how growing objects and plastically deforming objects and self-assembling objects shape themselves, in contrast to how we as humans assemble structures when we want to build them. When we think of man-made structures, we think of basic paradigms that are mostly centered around building blocks that seamlessly and perfectly fit next to one another. These structures, when they're built or when they are assembled, they require no strain, they fit perfectly, and the instructions tell you immediately what you're going to get. Another central paradigm is that of casting. And if here we take by hand every building block and we put it in its final position, when we're casting, we're sort of doing the same thing on a molecular level. We take every piece of material constituency and we place it where we want it to be at the end, and then we let it cool and solidify. Something that takes both of these things together and marries them is the concept of additive manufacturing. What you see here is the 3D printing of a house from concrete. So it has both notions of placing things in configuration space where we'd like it to be, and also a bit of the notions of casting. These paradigms of assembly have two main properties I want to dwell on. The first is that pieces fit perfectly next to one another. And the second is a bit outcome of the first, is that it gives us very predictable structures. If I give you the adjacency matrix, the adjacency map, I'm telling you which building blocks is adjacent to which other building blocks and what is their relative orientation, then you know exactly to tell me what the structure looks like. There's just one way to build these things up. Now, it seems that this is a very advantageous approach because it lets you reliably and predictably make something. However, there is a hurdle there, because that means in particular that if you want to build something very complex, then you need a very elaborate list of instructions. Okay, and in many cases in nature, we don't have that. We need something very complex to be generated from something relatively simple. How does nature do things? What you see here is an Arabidopsis plant growing. As I understand, I'm no botanist. Already at this stage, the leaf has all the cells it will have as a grown leaf. The actual cells can expand about 100 times in size just on this cycle that involves auxine translating to expansine, softening cell walls and allowing them to expand under turbo pressure. And what you see here is that it's not that the leaf says, okay, this leaf beat is going to be there. There's a leaf, and now some parts of it are expanding differentially compared to the rest of it. And out comes the shape. What you see here is an animation based on electron microscopy from Evan Nogales' group of tubulin heterodimers coming together to form a microtubule. And you see that there's a sheet forming. It's a saddle-like sheet that forms at first, and that sheet closes up and forms this microtubule. Again, I'm trying to make a tube, but I'm not making a tube by placing every building block in its desired place in the assembled tube. Instead, the building blocks themselves come together and they favor a relative positioning with respect to one another, and they favor a certain relative orientation with respect to one another. And again, the shape that we observe and experience emerges from those local interactions. Last of all is a movie that I hijacked from my colleagues in ESPCI, José Bico and Benoit Roman. And what you see here is a piece of torn plastic sheet. Okay, so this is just a standard piece of plastic sheet with, a logo still on it being pulled apart. And even though the process is very, very simple, you just take the sheet and you stretch it sideways, and there's no detail in the assembly, in the plastic deformation, and there are no oscillations in the plastic deformation. You see this wave upon wave upon wave in the structure of the boundary of this thing. Again, the actual shaping process was very, very simple. You just elongated plastically a very thin sheet, and out come a very complex shape. Now, this is in part due to the fact that thin sheets bend very easily compared to their ability to stretch. At this point, I typically have a piece of paper. I don't. Vince to the rescue. Thank you. So we know, especially in this crowd, that these thin sheets are very hard to stretch and very easy to bend. And consequently, if they do any compromise, it's going to be much easier to do it in the bending deformation compared to the stretching deformations. And it's this principle that allows these local, non-dramatic in-plane effect to manifest as these very violent undulations out of plane. And it's not unique to torn plastic sheet, this shaping principle. As a matter of fact, what you see here on the left is a beet leaf. So these sort of shaping mechanisms where things are essentially shaped by differential stretching or differential elongation are very commonplace. If these two just look similar, can we sort of induce the same deformation by mimicking the same process? Can we just differentially elongate the edge of a leaf? So this is an eggplant leaf onto which auxine was applied at the edge. And by day 10, you see a few undulations. By day 12, they become more violent. And by day 14, you have a fully wavy leaf. So these things follow very, very similar shaping principles. And in general, what you do here is you redefine distances locally. You don't tell this thing bend up or bend down. You don't tell this thing to buckle in a specific way. You just say, I've decided to add length to this two-dimensional manifold in a specific way. And out comes the shape. So heading towards the summary of this, when we're assembling compatible building blocks, then we primarily think of pieces that perfectly fit next to one another, and there the adjacency determines the shape. And what we have is the assembly of incompatible building blocks. So imagine forgetting your Lego bricks out in the car in August in the sun and having each of them distort in a different way. And then you take these distorted building blocks and you try to insist to compose a solid from those. Then you have to distort each and every building block in order for it to join the assembly. Now, it's quite natural that every distortion is going to be different. Moreover, even if all the building blocks are distorted in the exact same way, when the two first one distorted in order to fit one on top of the other, when the third one comes in, it's not necessarily the case that it could distort the same way as the previous two. There's a completely other state for the system now. It has to possibly distort more. So the system displays a highly cooperative ground state. And if we think of subsets of it, they satisfy different elastic problems. Please stop me. This is supposed to be as interactive as can be. And if you won't, then I'll spontaneously stop and we'll have awkward silences. Told you it would be awkward. How many of you know how residual stressed glass is, how tempered glass is made? Okay, fine. This is a Prince Rupert drop up here. It's an image of a tadpole-shaped blob of glass. You get it if you take molten hot glass. You need soda lime glass. You don't need Pyrex. So I can get to it later if you want. And dribble it into a water bucket. Essentially, you take molten glass and dribble it into water. And what happens is it solidifies instantly. And it has this property that even if you hammer its head, it doesn't break. But if you nick its tail, then it pulverizes instantly. This is, the extreme version of tempered glass. And we can understand how this was formed if we think of what was the process that happened when you took this hot molten glass and dropped it into a bucket of water. Okay, so what happens initially is that you have a droplet of glass. And then you heat it up. So now it's hot. And now I drop it into a bucket of water. There came the bucket of water. Okay, now only the outside surface cools. Now it cools instantly and it solidifies, but it solidifies in its current length. So whatever was the configuration of the droplet as it hit the water, that is the skin that is formed on the droplet. Now it cools. Now as it cools, the inner core, as it cools, shrinks. Because like all thermodynamically stable solids, it has a positive coefficient of thermal expansion. So now it's way, way too short for the circumference that it already has. Now this is solid. This is now solidifying, but they're connected. They don't form this gap. It's one giant solid. So what would it do? What it ends up doing is that the outside shrinks and the inner region sort of extends. And this is the state at which the solid forms, yes. It does shrink laterally, but just a bit. But it is supported radially by the pressure from the molten inside. In reality, there's a gradient of temperatures. And then as the gradient of temperature goes in, this is an oversimplified picture, but essentially, the boundary condition that the outermost layer sees relies on the pressure by the solid when it's very hot, by the inside when it's very hot yet. Okay? Okay, so there is a non-trivial stress profile in which the outside layer is under a lot of compression and the inside is under a lot of tension. Now, it's not a bilayer like it's imaged here. It's a continuous gradient, where the outermost layer is under compression and the innermost region is under a lot of tension. And now you can understand what happened when the Prince Rupert drop. You ask yourself, how does a glass break? So glass breaks typically by mode 1 fracture. That means that we're applying tensile stress. We're opening microcracks. Those are necessary for the stress focusing such that our applied force all goes to one place and then can propagate a crack. And if we have, to begin with, a very strong compressive stress on the outermost surface, then we cannot open these microcracks up. We don't have the ability to propagate a tensile force from the outside in and get amplified by these local stress focusing impurities. That explains why you harden glass this way and why it becomes more resilient to breakage, becomes more resilient to scratches. It turns out, though, that if you somehow get away and find a way to expose the interior of this place, if someone didn't tell you you should not drill tempered glass and you try to drill it, the minute you go through the compressive stress layer, you enter the tensile region, what happens? It explodes. It just shatters immediately. So your front windshield in your car is not tempered. It's a triplex glass. It has a plastic sheet in it. It's a different story. But your back window and side windows are tempered glass. Okay? So that function is crucial because when it breaks, you don't want it to break into large shards. You want it to break into these small particles. And the tempering tells you that once it starts to break, it essentially stretches itself. It breaks itself. Okay, so this is the story of tempered glass. Of course, the glass in your car is not made by being dropped into water. It's made in these sorts of machines. This is actually an Indian factory. There's a furnace there where the glass is heated, and then in this chamber, jets of air abruptly cool the outside. And again, solidify the outermost layer while letting the rest of it gradually cool and pull on it. And if you look at your back car window through crossed polarizers that are able to see local compressions in amorphous solids even, then you will see the pattern of the jets of air that were there cooling that glass. Of course, if you break it, you get a violent disintegration. This whole story about glass forming, about tempered glass, is not entirely about tempered glass. It's about a solid that simultaneously tries to be different things or objects of different lengths in different spaces. It's about a solid that if I break it up to 10,000 pieces, each of them is going to relax somewhat and adopt a shape that if I try to bring it back together, it would not come back together. It will be incompatible, if you'd like. Almost every growing tissue, to some extent, is that way. As growth is essentially a local process, unless you apply a load of feedback to make things relax, then you redefine distances, you redefine angles in a local fashion, and that what ends up happening is exactly this sort of scenario where things might end up mismatching. What we'll do in the upcoming few hours we have together is we will try to describe these things using differential geometry, and we will see that there's a unifying concept of how do you describe these objects that are shaped by local principles such as growth and plasticity using differential geometry of embedded 2- and 3-dimensional manifolds. We're going to look at the metric description of elasticity of 3D solids and of thin sheets, subjects that have been mentioned here before. We will briefly encounter the notion of non-Euclidean plates and a few other examples of frustration. So frustration, as we see it, come in a variety of flavors, and I want to show you at least a few of them because there are different ways in which things could not add up. And we'll probably also do frustration in 2-dimensional liquid crystals because it's a very closely related subject, even though it has to do less with growth. But time permitting, we'll touch about viscoelasticity. Any questions? Hi. So I think we're done with this. There's no specific textbook. There's the lecture notes I'm working with. I can perhaps work later on this week to make them available to you. I highly recommend this book by Struick and this review by Randy Kamian as sources of learning some different fundamental basic differential geometry. There's an additional reference by Pogorelov, but it's less widely available. Yes, and that's it for now. Can we get the screen up? The basic picture we would like to start with and start building our understanding from is that we've learned in standard elasticity. Is there anyone in the crowd who never took any course in elasticity? Okay. So the basic premise is that we have what we will typically mark in X is the rest configuration. And that is the state of the system in which the material is at rest. This is what it would like to do. This is where it is happy. And there's the deformed state. And we would like in general to think about it, not in its own right, but as a mapping from the rest configuration to the deformed state. Essentially, for every point here, we know to tell you where did it end up being. We can also define the displacement vector, which says if you take where you ended up minus where you started off, then that gives you the displacement vector. And finally, we get to the strain. Of course, if I have a uniform U, then it does not correspond to any elastic deformation. And therefore, just purely the value of U is not of much use, but rather spatial variations in U. And we end up with the basic strain, or the linearized strain, if you'd like, that looks this way. Now, in terms of what we will do soon, and in particular, things that have a bit to do with the rigidity ideas, if I have a three-dimensional solid, and at different places it has different orientations, then some place must have had a large rotation gradient in it. This is not the case for thin structures. So the material orientation here and here are very different compared to where they started. But no place within the sheet was there a large rotation gradient. So when we come to describe these sort of structures, the linearized elasticity strain tensor is not fantastic. It's easiest to see by showing that it is not capturing well large rotations. How many of you have seen this? About a third. So if R is just a rotation, so if my distortion amounts to just a rigid rotation, then r minus x, which is u, is just O minus I times x. And that means that u, which is grad u, is just O minus I. Which means that if I write now the strain, the linearized strain, I get 1/2 of O plus O transpose minus 2i's. And for example, if this thing was a rotation by 90 degrees, you know what, let's do by 45 degrees. Then this thing is of order unity. Okay? So I took the thing, I rotated it by 45 degrees, and my strain measure, which is a very nice strain measure, it's linear, it's very easy to work with, it gives rise to linear equations, is not a good measure. If we want to measure things locally and appropriately and make sure that we capture the geometry right, this is not a good thing. And of course, there is a way to amend this by taking what is known as the nonlinear strain. And to be honest, when first appearing in books like Landau-Lifshitz, this is the first guide that appears. This is the physical one. And this would be, say, page 2. Page 3 and the remainder of the book is this. Okay? So aside from peculiarities like Foppel von Karman and things that really require nonlinearities, we typically ignore this. We would not do this. We will keep on to this. And we will, as a matter of fact, we're going to reverse engineer this into that. So this is fairly familiar to anyone who's done any elasticity course. Okay? I'm going to now use the mapping that says u is just r minus x. So grad u is essentially grad r minus I. So what's written here is grad r minus I plus grad r transpose minus I plus grad r transpose minus I, grad r minus I. And when we continue this, we realize that what we have here is grad r here and grad r times minus I cancel each other out. Grad I there and grad transpose here with this minus cancel each other out. This minus I cancels out with this product, and this guy is the only one that remains. So we kill this. The only one that remained is this. Grad R transpose, grad R. If you would like, and I will do this constantly, even though many find this much less elegant, I just find calculation this way much more effective. I would write this down for you in index formation. And whenever we'll have an index appearing twice in a product, we're going to sum over it. Our R here is a vector that lives in our ambient space. It could be 2-dimensional, it could be 3-dimensional. It's always an Euclidean space in this case. And I is just delta ij. This is the strain. This is our fundamental quantity with which we measure distortions. And every elastic description that we know is a description that takes a quantity that measures distortions and gives us if you'd like, an elastic energy that depends only on how much distortion you have and on none of the history of the process that led to it. When we think of classical springs, the elastic energy is some constant L minus L bar squared. It means that the forces depend on the elongation. It's a linear function. It's very convenient. It turns out it also has very elegant mathematical quantities in terms of proofs. What happens here is a bit different. What is this? dir dot dir or djr. This is a quantity called the metric gij, and this is the metric, and it satisfies the following identity. If you'd like to measure the distances squared of an infinitesimal element in your coordinate space, then it is given by this sum. Okay? This is just as like saying that if you'll take dx1 squared g11 plus 2 dx1 dx2 g12 plus dx2 squared g22. This is the length squared. This means that fundamentally, G measures lengths squared. As a matter of fact, it measures length squared per funny coordinates. In our case, our coordinates measure length in the undistorted case. But as we'll see soon, you don't have to adhere to that convention. You could go to other conventions in terms of your coordinate. Questions? Yes. Yes, so we'll get to it soon. What we presently did is we just showed that the very standard elastic description we have is actually the metric of our present configuration minus the identity. And now we'll do a bit of differential geometry and some index gymnastics. And at the end of which we'll be able to generalize this to a general case. Any questions? Okay. How many of you, yes?
So the existence of a displacement field is only if
I can't.
the existence of a displacement field, defining U as R minus X.
Yes.
If you have, let's say, a two-dimensional link going out of plane, does it still work? It doesn't.
No. So this thing makes sense only when you start from a rest configuration, which is a certain case. And from that, we inherit a mathematical description of elasticity that is fully interpretable. And it's interpretable in these terms. And what we'll see is that what we'll end up with today is a different elastic description in which that is going to look very much like this, but does not start from that.
I think that's what I was getting to. So if something which is 2D initially and then it deforms out of plane,
yes,
you can't write that, but you can still write this because it has some metric which it deforms to.
Yes, so this is a three-dimensional metric in a three-dimensional world or a two-dimensional metric in a two-dimensional world. Yes, okay. In general, when I think of covariant components and contravariant components, I only do so in the setting of embedded manifolds, okay? And everything we're gonna do today is going to be sort of limited to the context of R3. So every vector we will look at right now would be a member of R3, okay? Now, in general, when we would think of the space of configurations, of R's of X's, this would be a configuration of a structure in R3, then this lives in some domain. And if I look at something of this sort, so this is the differentiation of R with respect to the ith component of its coordinates. So it has several coordinates that parameterize a certain configuration, and now I'm differentiating R with respect to that. Well, that's going to be some vector in R3. It's not necessarily going to be a unit vector. It's just going to be a vector. And if I now ask, if I just gave you coordinates xi that live on this solid R, and you use this to describe your structure R, then this is the basic structure that comes to mind, and this is a tangent vector to this. And then you can ask, well, what is the derivative of this guy? And if this mapping, if the mapping from the space of coordinates to whatever configuration I presently have, so this is no longer a rest state and a configuration. This is just a configuration and essentially some parameterization of this configuration. So this could be a solid in our space, and I say, oh, let's endow it with polar coordinates. So these would be polar coordinates, and this would be 0 to 2 pi, and this would be the damp. So these are just names I'm giving to points. And it turns out that once this is sufficiently smooth, then this mapping is regular in the sense that the three vectors formed by differentiating R according to the three coordinates are independent of each other. That means that they form, that they can essentially span space, and that every other vector, which is essentially formed this way, this is dj di r. Well, I can express it in terms of the previous triplet, and we call this the Christoffel symbol of the second kind. So everything here is embedded in R3. Everything is fairly benign and boring. And additionally, we can say that once we have the parametrization that we gave to our solid, that induces a metric. So if I look at EI and EJ, those are two tangent vectors. Those are DIR and DJR. Well, that's essentially GIJ, okay? EI is a vector in R3, EJ is a vector in R3. I'm taking the dot product between them in R3. Everything is well-defined and well-behaved. And when I look at things this way, I realize that this is not independent of that. Okay, I can differentiate this and get all the projections of the first derivatives of the unit vectors on the other guys. Okay, I do this 3 times, I fiddle with things around, I can end up with a definition that gamma ijk is 1/2 g k l DIGLJ plus DJGIL minus DLGIJ. There you go. This is the operating definition of gamma. It turns out that under this definition of the metric, you can prove this directly. And I did not yet tell you who is G with upper indices. G with upper indices is a completely different guy from G with lower indices. It's the inverse of G with lower indices. It's the guy whose product gives you delta Ki. So this is called the inverse metric. Now, all the structures that we so far have, we have completely inherited from R3. Yes.
I have a question because when preparing my lecture, I had confusion about that. So when we write this delta Ki,
Yes.
so delta with Ki at the bottom will not be a Kronecker symbol. I mean, this one is the Kronecker symbol.
Yes. So delta Ki assumes this shape in all parameterizations, and it's a mixed tensor. It's
Yes.
always 1, 1, and 0, 0. Levi-Civita as well. Levi-Civita, sometimes you need to multiply by density.
Yes, yes.
So this is, yeah, independent of the coordinates you use, this is what we have there. Okay. Now, everything I said started with the polar coordinates that I gave you here. I can now switch to a completely different set of coordinates, but describe the exact same body. And when you do that, then you employ some other set of coordinates, x tilde. Now you still describe the exact same structure, but you're doing now different coordinates to do that. And it turns out that if you can use the mapping that tells you what is x of x tilde, essentially, and if you define lambda ji as dxj by dx tilde I, then you can now define E tilde j, E tilde I, to be d tilde IR, which is just dxj dx tilde I times dr dxj equals lambda j I e j. All of these vectors now are still vectors in R3. I just changed the coordinates with which I wrote them. And now comes a major issue. If I think of a dot product taken between vectors, wait a second, I'm lost. Okay. If I look at any dot product taken between you know what? Let's keep it. Oh, you know what? Still do it. We can think of raising the index on this guy and defining EI tilde as the inverse metric GI tilde J, EJ tilde. Everything here is with the tilde. You can also define this without. EI equals GIJ EJ. And essentially what we do is we look at the collection of vectors that span our space, and then you can show quite easily that while EI was transforming with lambda, EI with an upper index transforms with lambda to the -1. So what we did so far is we employed polar coordinates. We described the body. We employed different types of coordinates. We described the body again. We had our little vectors that lived in the configuration space induced by our parametrization. And then there were other vectors induced by the other parametrization. And we learned how to relate them. And now comes the funny bit, which jumps from this thing, which is essentially freshman algebra, or freshman, calculus, if you'd like, and takes it to the more generalized setting. And in principle, sometimes some people jump immediately to where I'm going to go, and which is the following thing. If I have coordinates, and if I have all the list of tangent vectors here in the distorted configuration, in the configuration I'm trying to describe, and I would like to describe a third vector, this guy. It's the velocity of a particle that comes in and says hi. Because I have a collection of local vectors already at this point, induced by this mapping, I can describe this new vector in terms of those vectors. Essentially, if you give me any new vector, V, this is a vector that lives in R3. I can say, well, you know what? It has components that multiply the EIs. And it's going to be VI times the EI. Okay? Our EIs are the lowercase, our VIs are the top ones. Okay? These are vectors in R3. These are not. These are, if you'd like, scalars, but they're not quite scalars. Okay? These are the coefficients that you use in order to multiply this triplet of vector to form this guy. Now, what will happen if I change my coordinate system? If I change my coordinate system, then this guy will essentially become VI tilde. This guy becomes EI tilde. And EI tilde transforms according to that. V does not change because I changed my setting of coordinates. So essentially, V tilde has to transform correspondingly to this, because the product must not change. Okay? At this point, we have a leap of faith, and we say, if we want to describe this vector V, and all we have are these local tangent vectors, I'm going to stop describing V as a vector in R3, and I'm going to describe VI, the list of coefficients that multiply these vectors. And these will be called the contravariant components of the vector V with respect to these coordinates. Yes? Say again?
With the same basis vectors EI tilde, you are representing it with different components. Those are both EI tilde or
This
EI?
is tilde, and this is no tilde. And this is tilde, and this is no tilde.
Okay.
Point me to where the confusion is.
It's fine. Thank you.
Okay. Okay. The thing is, there was no thought that went into describing how these transform, okay? These are completely procedural things. We know how we define the EIs. This is how we define them. Consequently, we got a metric for free. We got a Christoffel symbol for free. We got how these things transformed as I changed coordinates, which is, if you ask a physicist, what is a tensor? Then a tensor is an indexed property. It could have 0 indices. That obeys certain transformation rules under changes of coordinates, okay? And if it does not obey those rules, then it's not a tensor. And that's fundamentally how we describe them. So the transformation rules are essential in the way we define these things. And from now on, we have to remember a few things. We will start thinking in terms of these tensorial properties, but these tensorial properties will be intimately related to the coordinates with which we use to define the system. One. Second, if we know what a tensor reads in one coordinate system, I can transform to another set of coordinate system, which is going to be curvy and crazy, and I know exactly how to transform it into that other coordinate system. I just use these transformation rules, and I get what are the new components in the new system, okay? So that is, again, a process that does not involve any thought on my side. I know how to calculate that. And moreover, if I write a tensorial equality, AI equals B J I V J, where I sum over the J's, and the I means that I have here 3 different equations. Okay, so this is a vectorial equation. This equation is going to hold regardless of the coordinates I used to define the local tangent vector with respect these components are defined. So if I now put tildes in all of these, this still holds verbatim. I don't have to change a single thing. Okay, so this is what we have to bear in mind when we come to describe the elasticity of these bodies under different coordinates. In the notes, I do a few index gymnastics. I don't think we need to do them here, but if you wish to, I think that that's a very good exercise. Okay. If we think of that true vector in R3 and the way it changed, then what I mean when I want to write things using our notation so far is that I would like to treat this vector using its coordinates with respect to our tangent vectors. And now it's just a chain rule. It just says di vj times djr plus vj di djr, which is di vj. Now this guy, we gave him a name, okay? This is djr plus, this was gamma. This was gamma ijk dkr. This entire thing is this. And then we have vj. Oh, look, well, because I'm on a blackboard, I can do the thing that's really fun for me and less so for you. I'm going to call this L, and then I can have the freedom to call this J and call this J, and realize that what I have now here is divj plus gamma j ik, if you'd like, ek. I just did it again. dj out. And this is what we generally mark as the covariant derivative of Ej. And it's nothing more than a standard derivative while taking into account the fact that the unit vectors or not unit, the vectors with which you use to define things in space move around. Now, this is how we differentiated the description with an uppercase index. If we have the same thing with a lowercase index, we end up having the same thing, only with a minus sign. Questions so far? Earlier on, I said that when we do an elastic description of a system, we're tempted to say that there's an elastic energy, which comes from an energy density, and that specific energy density depends on the configuration of the system, but does not depend on the path and the history of the object until it got to that configuration. So this notion, I think it was formalized by Trusdell, goes by the name of perhaps hyperelasticity. It considered objects that generally have an elastic description that comes from any elastic energy density. Turns out to be the most useful case to think of when you treat these growing objects. But it relies on you being able to properly define their configuration. I want to claim that if I give you the metric, okay, so here's a distorted object. This is my configuration L. This is my holy grail. This is the configuration my object is in right now. And I give it some coordinates just because I want to. So now you have this object with respect to these coordinates. This is the holy grail I have. What I want to claim is that if you have Gij, the metric, with respect to those coordinates, then there are certain conditions that allow you to reconstruct this uniquely. I claim that this G is a very good descriptor of this configuration, okay? Now, from a differential geometric point of view, almost everything I'm doing is fairly standard and fairly basic. But from a material science point of view, it's a bit different. I want to think of G as giving me gamma, okay? Gij gives me gamma ijk. So if you give me the metric and I'm allowed to differentiate, I can give you the Christoffel symbol of the second kind. If I have the Christoffel symbol of the second kind, I can now define di ek equals gamma ik j ej. This is a collection of partial differential equations defined over vector functions in R3 over our domain in X, okay? So the only thing that we do know is that there is some domain omega over which our coordinates live, and that's the only thing we know for sure. And this is what we're trying to solve for. This is what we have. If we have this, we have this. If we have this, we have that. Hey, you have a PDE, integrate it, you'll be done with. And of course, not all PDEs make sense. What do we have to have for a PDE to make sense? Remember the awkward silences? So we have to have a solvability condition. So this goes by the name of Frobenius theorem for various systems. What is the solvability conditions for this PDE? It turns out that all we have to claim to show is that if the mixed partial derivatives agree, okay, this is essentially like saying, okay, this is saying that we can think of this as a gradient, okay? So the question is, what is its curl? If you'd like, this is the equivalent of that. This solvability condition, if satisfies, allow me to integrate this thing in a path-independent fashion. Okay? So if this is satisfied, integrating this is path-independent. If integrating this is path-independent, it makes sense. But what does this mean? This means di gamma j k e l l minus dj gamma l I k e l. It says that this thing has to be 0. di gamma l j k e l plus gamma l j k di e l minus dj gamma l I k e l minus gamma l I k dj e l. di gamma l j k minus dj gamma l I k plus gamma l j k gamma I l m e m. I just translated this guy into that. Now I'm going to do the despicable thing of making L into N and making M into L. So I can throw this guy out, and then because I'm going to have to multiply this whole thing on the outside from with EL. And there's another gamma, which is gamma L I K, gamma J L M, it's EM, and then we do again this thing where the L becomes N's and the M becomes L's and the L comes here. Okay. This is that. And who's this? Riemann. I'm going to get the indices wrong, aren't I? So this is, I comes on the third place, and there's a J, K, L. No. L. Yes. There we go. Is it that way? Why do I have notes for? Okay. So the first derivative is the second index. There we go. And then, yeah, okay. This is the Riemann curvature tensor. That means that if you give me G, you give me a metric that uniquely describes the conformation of a solid, provided that the Riemann curvature tensor of that metric is 0. Okay. And now, if I do this integration, then I essentially integrate this thing. When I integrate this equation, it's a first order equation in EK. Okay? So I have to give it boundary conditions or initial conditions in terms of EK. So that those are the local positioning of EKs in space. Those amount to rotations. So once you set those, you set the orientation of your solid. But hey, EK is not the end of the day. Okay? EK is not my configuration. My configuration was yet related to EK by a more fundamental relation that said DIR equals EI. Okay? Hey, this is also a PDE. How can we know it makes sense? Well, it makes sense only if the mixed components, the mixed partial derivatives agree. It turns out that this is trivial because this guy is symmetric. Okay? So now when you integrate this, it is another first order differential equation that you have to give boundary conditions for R, which amount to translations. Okay? So up to rotations and translations, G gives you the solid uniquely. And now from the point of view of elasticity, we say, well, if we have an elastic energy that depends only on the configuration of the system, the principles of hyperelasticity say that if you want to describe a general elastic system, you need to describe the state of the system, the configuration it has, and write an elastic energy in terms of that configuration. And we just told us that if G is a flat metric, meaning it's a metric with a vanishing Riemannian curvature, then it itself suffices to describe the configuration very well. Now, our energy density will depend on a variety of other factors that depend on the material properties and on the actual structure of the object we're distorting and the elastic bodies, but are independent of the configuration. They relate to the body itself.
Effie,
Yes.
I have a question. Yeah. Regarding the integrability conditions.
This one?
Yes, both of them. Are there, presumably there are additional conditions if you're not simply connected?
Yes.
Do you know, is there a simple way to, particularly for the translational one, so for the second set, is it just the symmetry of the Christoffel symbols, or are there things that you can get that are
like monodromy
yes
restrictions? There are. I'm going to sidestep the whole issue. The minute you start thinking on non-simply connected domains, you could nullify all of this. So everything I'm thinking of, you should interpret not only in terms of in a simply connected domain, but also in some small vicinity of a point. So I'm not claiming any global claims. I just want things to make sense in terms of what are my fundamental unknowns. And in this case, the fundamental unknown would just be the metric. And then what can we say when we know that? Okay. And the thing is that this sort of approach that goes from the inside out says that if you know the metric, they can already say a lot about the system. one way of generating stuff in this way. The energy density, I'm deliberately not telling you what is the measure of this integral for a while now. The energy density, as we see it here, takes the configuration and tells you what is the energy density, the elastic energy density at that point. In particular, we expect every system to be able to relax locally, at least at a point. And in that case, the energy density is going to vanish. So there is some point which causes the energy density to vanish, some configuration. We say that if the energy density vanishes, then what the metric reads is something that we call G-bar. That is the reference metric. So now, at every point, we have two quantities. We have G, the metric, and G-bar, which is what it would locally like to be. And it turns out that the most convenient way of measuring the energy density is with respect to dV bar, which is the square root of the determinant of V bar and the volume integral. Yes. Okay, G bar, okay. The energy density depends on the configuration through the metric alone. Now there is, at every point in my manifold, there is a certain configuration that if G assumes that metric, then the energy density vanishes. W is an elastic energy density, okay? And G tells you how the configuration is distorted, okay? Now, there exists an undistorted configuration. There exists an energy density, there exists a metric which minimizes the energy density at that point. And it is that thing that we set as G-bar as the material property, okay? And you can think of that as the reference metric. Let's do something else. How long do we have? 10 minutes. Okay. Let's do something else. Remember that we took the tempered glass window and we threw a rock at it and it shattered and we got panel samples. When the window was fully assembled, it had a really strange reference metric. In different parts, it tried to be different things. Now imagine that you disintegrate this thing to a bazillion different pieces, each of which now goes, yeah, relaxes, okay? As it relaxes, it reduces stresses in it, and it assumes a much more relaxed shape. At this point, I take this tiny fragment, okay? And I look at it and I recall that it has some new coordinates. Okay, okay. It had the old coordinates x tilde, which were the coordinates it had while it was in the window, okay? Now I take it out and I let it relax. And it has relaxed, it's perfectly happy now. And now I say, you know what, you relaxed, you live in my Euclidean space, let's use Cartesian coordinates and have a look at you. So now, I'm doing it with a set of Cartesian coordinates. With a set of Cartesian coordinates, we already know what does the strain look like. The strain, let's write it bigger. The most natural strain would be DIR dJr minus delta ij. Okay? This is what my coordinates would like, my strain would read. which is just the metric it has with respect to the present coordinates. Yeah, I'm constantly jumping with this delta. Now the thing is as follows. As I took it out of the window and it fully relaxed, this guy is also that, okay? Now if I squish it in between my fingers, G will change, but what it wants to do will not change. Now I can go back in time and take all the fragments together and put them in the window, okay? And now each and every one of them used a different set of coordinates x in this process. So it doesn't make sense to keep a bazillion sets of different coordinates. Let's take our fragment and judge it with respect to the original window coordinates, okay? So it requires me to not work with epsilon that looks like G minus delta. It requires me to work with epsilon tilde. Now what is epsilon tilde? Epsilon tilde is nothing but the coordinate transformation of epsilon. It is lambda I L lambda J M epsilon L M. And what is that? That is just 1/2 lambda I L lambda M J G G L M minus lambda I L lambda M J delta L M. And this is just 1/2 G tilde IJ minus lambda L I lambda M J delta L M. And I take this entire thing and I notice the following thing. It is symmetric in I and J, it is positive definite, and it behaves like a tensor. I'm going to call it G bar tilde IJ. So the strain tilde, I took my fragment, I put it back in the window. Now I'm using the window's coordinates. Well, essentially it has this shape that the strain, which measures its deviation from what it wants to do, is actually the difference between its metric with respect to now the coordinates that go along the entire window minus this object, which is positive definite. It behaves like a metric, only while this guy I know for sure must live in my Euclidean three-dimensional world and therefore has a vanishing Riemannian curvature, this guy could be whatever. Okay? As a matter of fact, because the process by which I found these inverse mappings was for every fragment by itself, no one even assures me that this thing is continuous. This thing could be violent, could be as ugly as you could imagine. This guy is very well behaved. So now, wearing two different hats, the elastic problem we deal with could either be thought axiomatically from the standpoint of a general energy density that has some local zero, defined with respect to the variable that uniquely define the configuration, or saying we're building on linear elasticity We're building on everything we know. We just write everything tensorial and we pull it back to some other frame of coordinates. We go back to the set of coordinates where everything is Cartesian, and then we push forward to some other set of coordinates where things could vary in space. Questions? Yes? No. As a matter of fact, when I write their W in a general case, that's it. I didn't even tell you what was the energy here. I just told you that epsilon is a measure of distortion, meaning that it is 0 if and only if there is no distortion. And that's it. Okay. Now,
I have another.
Yes, please.
When you define W,
yes.
I mean, is it obvious that we have to use the reference, I mean, the reference metric, the rest metric to integrate it?
The measure.
Or is it just a choice?
It's a choice. It's absolutely a choice. So just to be clear, this was an energy density. The question is density with respect to what? I could use unit volume in the configuration space. I can use unit volume in the reference configuration space. I could use, anything else. And it turns out that if you use the current configuration measure, everything is still viable, but the actual quantities you get from this becomes a bit ugly. So right now, what's defined there is the Cauchy-Green strain. What you would get if you vary this W, the Frechet derivative of this thing, becomes the second Piola-Kirchhoff stress tensor. It's a symmetric quantity. It's very elegant to work with. If I change the measure to be dV instead of dV bar, you get the first Piola-Kirchhoff stress tensor. So everything is still thermodynamically valid, only the quantities you work with stop being symmetric. Okay, so some cases here, what I showed you are choices. The other ones are, rather free. Yes? Okay. Yes. Yes, but there's another caveat. The caveat there is that just so we don't get this conversation to ourselves, also because I want to learn, there is a debate running, I think, back to the 70s between additive decomposition of growth and multiplicative decomposition of growth. And in a sense, what we have here is something that follows a bit more the additive decomposition of growth. Okay, what I want to say is I don't think about this as a decomposition of growth at all, because I don't know what was this thing before it was G bar. And that is a crucial part of our description. In the additive, in the multiplicative decomposition of growth, what you do is you consider the quantity which is essentially the gradient of F. And then you say, well, this is composed from an elastic component and a growth component. And now the product has to live in our space. But the product was the result of an initial growth that took you from where you started to where you want to be, and then was subsequently how you took where you wanted to be and ended up in where you're at right now. And this, the elastic energy, if you'd like, it depends only on the invariant properties of this elastic composition. And the comment here was that this, to some extent, could be identified with that. It's true in a sense, if you know where you started from. In our case, and what we'll see in many other cases, this could be defined even when you don't know how you started. This requires you to have some history on the formation of the object, where this is sort of sidesteps it. Either way, you could still work with this in this sense. To some extent, this is just the square root of that. There is equivalence. But I think that the main advantage between this and that description is not so much in the constitutive laws, and in as much that it maps the problem to an optimal embedding problem. And then things become, yeah, you have the machinery of differential geometry at your display. Yes. Yes. So just the last thing for us to say before we break is, after we define the strain, one can define an elastic energy density that would be where this thing depends solely on material properties and properties of the manifold, but not on the configuration. And all the dependence on the configuration comes from here. So this is now assuming epsilon is small. Okay? This is now the second order expansion in tensors in a series of much longer. And once you write things here, I think it becomes much easier to show the equivalence with that. Okay. Thank you. I want to start with a question to you. Was this lowballing? Was this too slow? Was this making sense? Was this too fast? Was this too slow? Would you like to see more advanced things going faster? One vote for slow. Well, I do not get offended. I just want to gauge myself. I was gearing up for a heterogeneous crowd, and I don't know what your backgrounds. So some of you know this by heart, and this makes no sense. As a matter of fact, some of you are upset by the fact that they only use embedded objects. But for some of you, this is new. So this will get gradually more sophisticated in the upcoming 2 lectures. Okay. Thank you. Okay. Yes, go for it.
Regarding this, like the analogy between the growth deformation, like F transpose F equals,
the multiplicative decomposition?
Yeah. No, I'm asking, so this G bar, supposedly this will be our rest metric. So I mean, if we want...
This is the reference metric, yes.
Yeah. So if we want to do this, we need to have like a map between, from a sort of a reference configuration to our rest configuration, I mean.
Say again, we need to have a map from?
From the sort of a reference, or like any like configuration of our choice, a reference configuration to our, what we take as a rest configuration, this G bar. Supposedly the stress should be 0 at G bar, right? Like,
yes, okay. So indeed, the stress vanishes when G equals G bar. You can formalize something equivalent between F growth and the F elastic. For example, if F elastic would be the identity, then you satisfy exactly what you did with the growth. In the literature of the multiplicative decomposition, the term they use is virtual configuration. I think that the appropriate thing is not to think of any configuration, okay? So essentially, what we'll do next time is we'll write this thing and we'll immediately change coordinates. We will make sure that we remember the following things. Remember that I told you that G measures distances squared? When we started with G writing G and delta, delta was lengths because it was lengths measured in the undistorted configuration. Now this becomes G bar. The coordinates I'm employing could be crazy. And when I teach this, I always tell the students, that G measures length squared per oranges apples. So it measures length squared per your coordinates dimensions. And once you use completely crazy coordinates, then the description of here remains invariant, because whatever crazy coordinates these has in the denominator, this has in the numerator. And once you multiply, you get scalars and everything becomes coordinate independent. Whereas when you're working with this, you're sort of obliged to work with the notion of distances and still think in terms of sort of configurations. You could depart from that because eventually, mathematically, I think the two are equivalent. But it's easier to depart from this description when you look at this, when you allow your coordinate to be anything you'd like.
Follow-up. I've read some formulations of, like, they call it incompatible deformations,
Yes.
where they consider a body to be like a reference body, and it has like a reference configuration, which is not necessarily stress-free, and it has an actual configuration. So I mean, like, what I'm asking is it possible to sort of like describe G bar? I mean, how do I, like, is it possible to have a sort of like let's call it a reference, like a body from which I can generate this G bar, basically? How do I get an expression for G bar?
I will think of coordinates of my configuration, and then I will ask what are the locally preferred lengths in those coordinates. So for example, think of, I think we're gonna probably do this next class. Think of the tempered glass example, okay? So this is what it looks like, but what we know is that the outside is too long compared to the interior. Let's cut it on the side. What you think we have, okay, this is a crude, you know, discretization of the thing. You have very long circumference. You have a very short inner core. That is the length in the y direction, and it changes along the x direction. So now, if I use a three-dimensional metric that captures this variation and say this is G bar, then I captured what it wants to do. Now, the actual problem is you stretch all of these, you glue them together, and then you tell them, now you're a solid. Figure it out. And the elastic problem we're faced with is trying to figure that one out. And when we do, we ask what is the flat metric, the flat configuration that best approaches what this thing wants to do. Now, in cases where this is compatible, where the Riemannian curvature tensor of this is 0, this does exactly that. And all the interesting stuff that happens through growth, that happens through deformation, this will have non-zero Riemannian curvature, meaning you cannot make it. You can only find approximation or find compromises that approach it. Did I answer? Yes, please.
You can make the connection also a dynamic degree of freedom, because so the connection itself to be a dynamic degree of freedom, in the sense that you now insist that you use the Levi-Civita connection associated with the metric, but perhaps, you know, you have some other connection in the growing
yes.
body which has some physical significance, and you might want to set that to a reference configuration or something.
Thank you very much. So the basic question was, this guy, which we inherited from the metric in a very specific recipe that goes by the name of the Levi-Civita connection, is a very particular choice. In general, gamma tells us how to advect these local tangent vectors in space. What I will be talking about are purely Riemannian structures. And Riemannian structures, in that sense, don't have anything but lengths. Consequently, I will only talk about the Levi-Civita connections. Just to give the rest of you an idea of what we're talking about, if you think of a crystal, then a crystal has natural notions of directions in it that are independent of lengths. So say I have a square lattice, and then all the particles that are to my left, I can point to them. Even if someone sort of stresses the solid a bit, so perhaps it's a bit up, I can still figure out quite uniquely who is the particle to my left. And now if I'm saying, well, let's choose EI or E1 to be the vector pointing from you to the particle to your left. Now that's a different choice of local directions that is not induced by lengths. Now, it turns out that if you now perform crystalline defects, then the whole notion of these directions messes up in space, okay? This would lead to the notion of Cartan torsion, which in our case is completely zero, and we don't want to deal with it. As a matter of fact, from my experience, in most amorphous cases, such as growth of tissue and plastic deformation of amorphous solids, it's completely immaterial.
It's just to clarify, when you did the calculation of this that is here about the compatibility of this gamma.
Yes.
So the conclusion is, I'm not sure that I got the conclusion right. The conclusion is if the Riemannian tensor is zero.
Yes. The conclusion was the following. If I give you a metric, then that corresponds to a configuration. So this is a metric with respect to some coordinates. And that configuration is unique up to rigid motions only if the Riemann curvature tensor of this metric is zero. That was the definition. So R is a configuration in R3 if and only if the Riemann curvature tensor of this metric vanishes identically. What troubles you?
No, the plane.
The plane.
Planar metric.
What?
A planar metric.
The
Just
planar
the
metric.
identity. It has many embeddings because that are not identical up to rigid transformations. Oh, it's a,
this is a
3D
3D solid in
3D
3D
okay.
space. By the way, I can claim the entire thing, and we'll do this next in 2D. I'm just going to give it different coordinates. I'm going to call GA, and I would say that it has a two-dimensional. And this would correspond to this only if this, so 2D in 2D is also, you can deduce a configuration into 2 dimensions from a metric if and only if the Riemann curvature tensor of this metric vanishes. Now, here is a parameterization of the plane. I can calculate a metric from that. It's going to be a certain metric. The Riemann curvature of it will vanish. And I can now look completely different parameterization of the plane. It will be completely different coordinates, completely different form for A, but the Riemann curvature still vanishes. Okay, so there are many, many different ways of describing the same structure with different coordinates, but what all of them have in common is that when I calculate what happens to the Riemann curvature tensor, it vanishes. And once you have a metric whose Riemann curvature does not vanish, it cannot describe a configuration in the plane. No, it cannot describe a surface. If you're looking at a simply connected domain, it does not describe a configuration. If you try to integrate the equations that give you a configuration from the connection, by integrating different paths, you would get different results, which means that the result, that the PTE is nonsensical.
About unicity, provided it exists.
Oh, all of these results are unique up to rigid motions. So what you had was a PDE
Well, yeah, it needs to
And
be
all you
integrated.
had to do is choose the initial
Yes,
condition.
yes, yes. I mean, this is for spaces in the same dimension, left and right.
Yes, and these are spaces in the same dimension, 2 dimensions in 2 dimensions, and 3 dimensions in 3 dimensions.